Welcome here on this HERCULES specialized course. I will speak today about scanning electron microscope and focus ion beam. So thanks to Corneliu Gica, you have some idea about electron microscopy. So I will go just really briefly through some theoretical stuff, and then later on I will be more focused about focus ion beam and gas injection system, and also about practical stuff, and I will show you how to use microscope, what we are able to do and what we are not. So go on. So I'm coming from Prague, so you had already possibility to hear Mikhail Vorekta today. We are from the same group, from nanomaterials group from Charles University in Prague. So we are settled in a very beautiful city. So our group consists of two structures. So it's nanomaterials group here in Charles University in Prague, and material science beamline at the synchrotron Electra. Our research is focused mainly about nanostructure catalyst, motor catalyst, and hydrogen technologies research. So I will show you a few examples. So it will be mostly about samples which are using as a model catalyst. Also, we are studying materials for nanobiotechnology and sensors. So also I will speak about that. So go on. So today I will speak about two microscopes. So I will speak about scanning electron microscope, and then about the microscope equipped with focus ion beam. So as it was said in the morning lessons, when we have an interaction of an electron beam with a sample, the incident beam then emit several different electrons, several photons. So what we are able to detect, they are secondary electrons, backscattered electrons, X-ray, Auger electrons. And if the spacement is transparent for an incident beam, then elastically scattered electrons, direct beam, and inelastically scattered electrons. While for transmission electron microscope, you're able to see all of them. For scanning electron microscopy, your samples is too thick, so you have no possibility to see a transmission beam, only electrons which are emitted back forward. So they are secondary electrons, backscattered, X-ray, and Auger. So I will go just briefly through them, as Corneliu already said a lot about that. So secondary electrons are electrons which are inelastically forward scattered electrons. So the initial beam interact with atomic electrons, and they are escaping from a very small escape depth, as you can see on the image on the right side in here. So from that reason, you have an information about the surface structure. So we are speaking about topographical contrast. Here you can see an example how this topographical contrast looks like. So moreover, you have what we call edge effect. From the edge of the sample, we have more secondary electrons are more emitted. So you have a vector signal, so they are looking brighter. So that's topographical contrast. On the other hand, you have backscattered electrons, and they're elastically forward scattered electrons, which interact with atomic nuclei. So we can have information about chemical contrast of a sample composition. Information depth, it's much bigger, so it's about 10 to 100 nanometers. However, the emission of backscattered electrons, it's not so high as a secondary electrons. So we have a smaller number of backscattered electrons, and the signal has lower intensity, and it's a bit more noisy. Where to use secondary electron and when to use backscattered electrons. Here we have an example of tungsten oxide nanorods on mica. So mica, it's a non-conductive sample. From that reason, we have a charging effect. You can see this charging effect on the image on the left side by some, like say, clouds or this bright clouds there. So image on the left side is taken by secondary electrons, while when we are using backscattered electrons, we can eliminate this charging effect. And you see a nanorod structure on the right. So let's move on to X-rays. You already heard that we can detect a chemical composition of a sample. So the process, how we can obtain them is that primary electron beam interact with an inertial electron. It's transit this electron to higher energy orbit, and then there is electron vacancy left. So another electron is filling this vacancy by making a downward transition. So we have the excitation process, and this excitation process is released by characteristic X-rays. So then we are able to study chemical composition of a sample. An example you have on the right side up there. So there is several of them, like aluminum, chromium, iron, etc. The information depth is even bigger. It's about hundreds of nanometers. So it's not, let's say, okay, it's surface sensitive, but it's less surface sensitive than secondary electrons. You can go deeper. I will not speak here about Auger electrons because these Auger electrons are not very common to detect them in secondary, scanning electron microscopy. So here about the second scanning electron microscope construction. So the main part is electron gun. This electron gun is built from cathode. The cathode is, we can have several types of it, and by principle of emission of electrons. So it's thermo emission, field emission, or Schottky. So Schottky is combination of thermo emission and field emission. From that reason, they are using different materials. For cathode, mostly it's tungsten or tungsten coated by Zircon Oxide. So it's where electrons are emitted. After that, we have a first cylinder, first lens. It's a Reynolds cylinder. The function is to control emission current and to serve as a convergent electrostatic lens. Further on, we have several structures, several electromagnetic lenses, and their function is to convergent beam or to correct the stigmatism. And The first of them, it's called extractor. On an extractor, we have positive potential to accelerate the electrons, and the energy of these electrons, the electron beam energy, could be in a range from few electron volts to mostly to 30 kilo electron volts. After all that, we have deflected lenses. The function is to scan on the surface, on the sample surface. So we are moving there and back by these deflection lenses to have image of our sample. So as you heard about it already, I will not go further. If you will have any question, do not hesitate to interrupt me in the middle, because to make it as interactive as possible. So now I will move to interaction with an ion beam, because it's what we didn't heard yet. So if you have a primer ion, ion is has a much higher mass than electron. So if ion interact with a solid, with our sample, there can be several processes. So first, it can sputter also electrons or a sputtered particle, ion or a neutral particle, or it can be implemented into the sample. So here you have a terrific equation. Just one thing which you have to remember from it, it's that is mass dependent. So it's it depends on a sample structure, on the material, and that it leads to mostly to two processes. So we have sputtering process and ion implementation. So by ion beam, we can sputter material, so we can create its structure, or we can implement ions into the material, so to enrich our sample by ions. Here, just as I said, that you have to remember that it's dependent on energy and on material. So most of the time they are used gallium ions as a source of in a focus ion beam. Here is an example. If you have a silicon as a substrate, so when gallium ion interact with silicon with energy of 30 kilo electron volts, you can see that this implementation depth is about 500 angstrom, while when you compare it with copper, is about the half of it. Also important is an incident angle. So here is a perpendicular, while when we are on a 98 degrees, so we are just slightly touching our sample. Also, the implementation depth is decreasing. On the right side, you can compare the initial energy, 5 kilo electron volts with 30 kilo electron volts. So also, it's the implementation depth is lower. This is what we can use for creation our same structure for ion beam milling and so on. Down there, I put here same charts where gallium interact again with silicon or with copper, and it's angle dependent, and we have a sputtering yield. It means it's about the amount of particles which are milled away. So the sputtering yield, it's increasing again when it's perpendicular, and it's increasing with energy. Here you can compare this incident angle. So about the construction of focus ion beam, I will show it to you later on here on the real microscopes. So just briefly to go through it. So focus ion beam, the main part is called liquid metal ion source. You can see it on the right side. So it means that, as I said before, the ions which are used are gallium most of the time. So gallium is in liquid form. Down there is a tungsten tip. Gallium is heated in here, and it's going down through the tungsten tip, and on the very edge is formed in a very small very small part when it's then emitted by extractor again. So next part, it's extractor cap. I will go, no, it's not there. So it's extractor, then the beam is emitted. So again, energy is most of the time from several electron volts to 30 kilovolts. And then similar as for electron beam, also we have here several lenses for convergation the beam, and for scanning as well, deflection, octoball, and so on. So I will show it to you later on in a real system. So here is an example. How does it look like in a chamber? Most of the time, the construction is that we have a dual beam. So it means the scanning electron microscope is combined with focus ion beam. And between them is 55 degrees. Most of the time, it's just dependent on the construction. So you are moving with a sample to be perpendicular to the electron beam or to the perpendicular to the focus ion beam. On the image right there, you can see also the gas injection system. So you have possibility to insert different gases into the chamber in the same time while scanning. This gas injection system makes you able to create structure, not to mill the structure, but to create a new structure by ion beam induced deposition or electron beam induced deposition. So it means that we have a precursor. You can see it on the picture on the left side. Here we have a precursor. So it's, for example, platinum with organic atoms, the mixture of them. It's bringing into the chamber, and at the same time, when you are scanning on the surface, you decompose by ion beam or by electron beam, you decompose the precursor. The organic atoms are pumping out by vacuum system, and the purified platinum is staying on your sample. So I will switch to several examples, but I will show it to you more deeply during the real operation. So here is an example how to mill or how to remove material by focus ion beam. So the sample was used tungsten tip. So we use it to manipulation with some carbon nanotubes. Unfortunately, with this tip, we weren't patient enough, so we make it, we destroy it. So to make it thin again, you can see it how the material it's removed. So just by very simply cutting from side. Unfortunately, such prepared tip is still too thick. So here you can see it one more time how it's curved on the upper part. It's again tungsten tip. So when with noise as well. So we fin it to a very, very sharp tip. It was about a few of nanometers up there. So you can use it later on for nano manipulation again. Another example, how we are using this focus ion beam, it's this ions implementation. So it's gallium enrichment of silicon, and then it was further electrochemically etched. So by this electrochemically etching, they are created pores, as you can see on the left side on the image in here. And by gallium enrichment, the places which were enriched by gallium were etching better, were etching faster. So here they are the holes which are created with this gallium ion beam. So they are more homogeneously, they are better separated, and they are more homogeneous in size. Then this sample was studied by tomography and topography. I will show it to you. How is it? So tomography is about the cutting layer by layer. So we are going through the pores. We are able, with ion beam, we are removing very thin part of a sample. So we go on through the structure. Or we use topography. So we are removing material from the very top, and we are then doing a reconstruction. So you can see how deep are your pores. So if I will go back there, then by using a software for tomography, so we can do a reconstruction of the of those holes which we created. So not about just material science we are studying here. Sometimes we have a life science. These are neurons on a microchip. The goal was that there will be great good contact between a chip and a neuron cell. So on the image of the left side, you see a neuron cell, which we protect by this gas-induced, by this ion beam-induced deposition. And then we did a cut, so we are able to see how good this cell sit on a microchip contact, which you can see down there. Here you can really see nicely material contrast, as the protective layer was platinum. This microchip was a gold, so it's bright, and here is carbon. But most of the time, we are working here on a preparation of TM sample. As Cornelio said on the morning, that to create TM sample, it's sometimes a bit tricky when you have thin layers. So you can use traditional methods, which are most of the time it's to create a sandwich. And this sandwich, you have to cut it, you have to polish it mechanically, then electrochemically, then to polish it by ion beam. Most of the time it's the argon ion beam, and you are creating a hole there, and you are studying the sample just around the hole which you were created. So it's time consuming. It's taken about 2 days, while to prepare TM sample as a lamella by focus ion beam, it's about an hour and a half. So here in our department, we are studying materials for proton exchange membrane fuel cell. And here is an example of platinum doped cerium oxide layer on carbon foil. So we have nicely porous structure. However, by scanning electron microscope, you see only a very top. So if you would like to see structure, how does it look like, how the morphology looks like, so you need to cut it. So I have just a example here that is like a top of the cake. So you need to cut it to see what's inside. So here is the process, how we are creating it. So this is your surface, your sample. So back there. So not possible to stop it. Wait a minute. Not okay. So I will go through the process faster, and then I will say to one more time to you. So here we have this gas nozzle. So we are creating protective layer to protect the surface. Then we are milling steps from the side to remove material. Then thinning it a bit that we will be able to cut it from a side. It's now, and to cut it from the bottom. So here you see how does it looks like. We are coming with a tip, we fix it on a tip, we cut it from a side. This is the most critical part. We are picking up, putting on the holder, fixing it there, remove it, and it's done. Okay, it's not completely done because it's still too thick. So we need to thin it again. So by again, by focus ion beam, by polishing, it's very gentle. Also, we are changing this we are changing the collision energy, and also we are changing the angle, the instant angle. So we can be very gentle to thin it down to several tens of nanometers. So it's transparent to transmission electron microscope. So here we have these processes again. Just it was too fast, so maybe on the left and down here is a holder. I will show it to you again today. So this is a holder you can put there. The main advantage is that you are able to put there 8 samples in a row. So for your TM station, you don't need to put it out, put it in, pump it, wait for good vacuum, and so on. So that's it from the presentation part. So I will stop sharing the screen. So, and now I will move to a real part where you will see how the samples real looks like and how the microscope works. So now I hope you see me, or still not yet?
No, not yet.
Yep. So there should be a problem. We'll stop the video, start the video again.
Yes, now we can see
it. Okay, cool. So now we are in a microscope laboratory. So I will show you, here we have 2 microscopes. This one, it's both of them are from Czech. So this microscope, it's called Mira. So it's scanning electron microscope. So it's the first one in which we will working with, and then over there we have the second one. It's again from a Tuscan company, and it's called Lyra, and it's equipped with focus ion beam. So I just will maybe clear the camera because it's a bit blurred. Just wait a minute. Hope better. Okay. Okay, so I will go through the parts. So I will speak at the beginning. I will show you how the microscope looks like. You see this online version is terrible. It will be better if you can be here. So on the very top, we have the cathode. So here is a column where there is a huge high vacuum. So it's 10 minus 8 Pascal there. So there is there are a few lenses for convergence, to make the beam as convergent as possible, so as small as possible. And then we have several detectors in there. So the scanning, for secondary electrons, we have one which is called in beam. So it's inside the chamber. It's not visible from here, but the second one is from the side. It's mounted from the side to make even this topographical contrast, to make it even more pronounced. Then this detector is backscattered electrons. It's not mounted all the time it should be mounted by hand, there and back. I will show it to you that also later on. And we have EDX detector from Bruker company. So it will be a bit more noisy as I will turn the microscope on. Because there is a pumping system, for sure, it should be a vacuum. So while the HV units will go on, I will show you how the samples looks like. So it was said for TM, the samples should be really thin, and preparation takes a really longer time. While for scanning electron microscope, it's much more simple. So here I have a holder, it's traditional pin. And you just place a pin and mount your sample there with carbon tape. So, for example, I will take something what is really big that you can see it. I have already carbon taped here. So without any preparation, here is same thin layer sputtered by magnetron sputtering, and you just very simply place it there. Okay, fix it that you are sure that it's not fall down. That's it. So preparation of samples for scanning electron microscope is very fast, and you can study whenever you want. Just you have to think about it, that it's better when it's conductive. We are also able to see non-conductive sample, but it's just a bit more tricky. So I don't know from which kind of field you are, what are you studying, if it's material science or life science, but sure, you can study also a life science sample, just they have to be dry, and also a non-conductive, and so on. So very simple preparation. So I will move to microscope again. Then when your samples are ready, you will open your chamber. We are waiting just for pumping system. So it's done. So when you will open your chamber, do you see it? Just remove this. So here you have a holder. You can put, like maybe like that. It's better from the bottom part. Here is a holder. You can put there 7 samples in a row. Better. Like that. I put there already something, but I just will show you how fast it is. So you're taking your pin, placing there and fixing, that's it. And unfortunately, you cannot, by this camera, you cannot see anything in the chamber. So I will show it to you by a chamber view in a microscope. So just wait a minute. We will remove that one. Because it's impossible by that camera. And I will pump it. So I will switch here. Okay. So now if it's running well, you see a computer of a microscope. So as I said, it's a test scan one. And here we have a software. So it's really user-friendly. Here, it's your holder. You can name any of them. So you know in which position what you have. Now we are waiting for a vacuum. So in a column, there is a 10 minus A in a gun pressure in where the cathode is placed. It's 10 minus 8 Pascal. In a column, it will be 10 minus 2, the same in a chamber. Here's a chamber view. As I said, by this online version, you cannot see in the inside the microscope. So by this chamber view, this one, it's the ion beam, the electron beam. So it's the end of the column. From the side, it's mounted scanning electron. And this one, I will move it with it, that you will see that it's moving, and that is it's going there and back. So it's for backscattered electrons. So now you can see how it's moving there. So now I will place it back. So till we will wait for a good vacuum. Any question for now? Not yet? Okay, cool. So we have our samples in. So at the very beginning, I will show you just a few examples. I have a Zircon Oxide balls there, then some mixture to do EDX, and a mica to have something non-conductive. So it's very fast. I will put only beam on. This is our second sample.
and you already have your picture there. This is your surface. So you have information about how does it looks like very fast without any preparation, it's not time consumption, so it's really fast method. So I will move to this zircon oxide. So we have zircon oxide balls. Just it's a bit. I have to focus. Focus is done with different working distance. It's too bright, but you use only outer brightness contrast and it's done in a minute. As I said, it's very fast and very user-friendly. So we are going closer because your balls are smaller. And now you can see this effect that I'm moving and the ball is changing to ellipsoid there and back. So it means that your stigmators are wrong. So I have to adjust a stigmator lens. Just a bit, like that. And you have quite a nice picture of your sample. You see that there are different balls with different size and so on. We are now in a detector, which is called here a secondary electron. So it's mounted from a side. I will switch to in-beam detector. So it's one which is in a column. And I will go much closer to have better image, to have better resolution. So I don't know, this one. You see how it's moving there and back. So we have a problem with stigmator. So I will adjust it. I will do just simple adjustment. And we'll go even closer. Okay, now it's going better. Just a bit. So now you can see even the structure of a ball, not just the big one, but also the smaller one, that there is the same structure of it. So this zircon oxide, it's not not smooth, but there is a same structure there. So one more time, it's very fast. If you would like to move to another part of your sample, it's very simple. And you check if it's homogeneous. Okay, for example, here again, and you move there and back just in a second. And then if you are satisfied what you've seen, you acquire an image. That's it. So it's really, really fast method how to check your surface structure. So this is a secondary electron. So I will move now to backscattered electron. So if I will change the sample to the Mica one, it's a non-conductive sample. So you see this charging effect here by those clouds of charge. So it's changing every time. So we are not able to see here very much. So I will change the detector just for a bit, but for secondary electron one, not an in-beam, but still we have this charging effect, and we are with a smaller magnification here. When we are going closer, it's getting worse and worse, and image is changing under the beam. So to eliminate it, I will move vivid. So we have this charging effect. So to eliminate it, we can eliminate it by backscattered electrons because their amount is really small. So if you can check a chamber view here, I will move with the detector under the beam. Okay, so we are here. And just by simply switching it to backscattered electron, you see that we really nicely eliminate this charging effect. So it's not only for material contrast, because for this material contrast, I rather use EDX to have the directly idea of composition, not only material contrast. Something is heavier, so it will be brighter. Something it's less heavy, so it will be darker. But by EDX, you have this composition map. So I rather use backscattered electron only for this charging effect elimination. So I will put it out. Also, there are several stuff like you can use both of them. So you can use mixture. I think that's one. So you have at the same time, you have secondary electron image and backscattered electron image. So back there. So secondary electron, and I will move with this backscattered detector. Okay, so here we go. So the last sample, it's some alloy. It's lots of different elements there. So, and you, I forget to put zoom on the CERT computer. So probably it will be faster when I will start the video and turn it on this computer. You see it? So, and I will turn on the EDX software. So, yes, you don't see it here, but I will move with a detector to acquisition position. So nothing interesting running now. So, and when you have not even a glue, what is in your sample, you just put acquire and directly you have a spectra there. Okay, let's stop it and let's quantify it. And by auto quantification, you have an idea that there is a, okay, I apologize that I forgot to put the software. Yep, sorry for that. My computer turns off, so you didn't see the map, did you? No, you didn't, sorry for that. So, or when it stopped, do you have some idea when it was? Did you check the map? Anyone? I guess, are you there? Can you see the map now? So it's element map. So I don't know when the video was stopped.
Before the elemental map, actually, we saw the image of SEM, and that was all.
Oh, okay.
Actually,
okay.
It freezes the scan, so.
Okay. Sorry for that. I really apologize, but it was my fault. So, did you see the spectra? Yeah, did you?
No, we haven't seen the spectra.
You didn't see the spectra as well. Okay, so only as I was scanning the sample. Did you see the sample before? Yeah, when I was sharing the screen here.
We saw half of the sample and then it froze.
Yeah.
Okay. So I will share the screen here. This one. So here you see the Tescan software. Yeah, do you see? Right? Or no? Are you? Yep. Oh, okay. It just freeze. Yep. Okay. So now, so here is your sample. And as I said, that if you have not even a clue what's there, so you can scan it in a minute. So when I will put acquire here, you have a spectra. Probably I have to remove everything. That you will see it, how fast it is. Okay, so you have a spectra, so we can stop it for now. We don't need something really great one. And we put on the quantify and auto quantification. And by auto quantification, you have really an idea what do you have in there. So it's copper, titanium, calcium, and aluminum, for sure, oxygen and carbon there. So this is the first insight, what is in your sample. Then you can even quantify it. So you have an amount of material. I just was saying that you have to take it not like very fixed, just same, how to say, not very precise number, just to have an idea that you have a 50% of titanium there and so on. And then I was showing to you that we can take an object. And if you would like to know where is what, so you can acquire a map. Again, it's very fast. So you're acquiring your picture here. You are choosing, just a minute. This has to be done. Okay. You are choosing an area where you would like to scan. Come on. This is not the user-friendly software to say. So you can change it. And then you put there the elements which you want. So it was aluminum, copper, titanium, and calcium. And you place acquire. For mapping, I would suggest to let it acquire for a few more minutes. But even from a very first scan, you can see that you have titanium rich areas and titanium pure areas. So these titanium poor areas are this, how to say, this messy one, so grained boundaries. While for copper, it's opposite. These grain boundaries are full of copper. Calcium is similar like titanium, so these grains are rich for calcium and boundaries are not filled with calcium. So if you will run it for several minutes, you will have better and more clear map because it's stable. So I will stop it here now. And then you can play with a software like that you would like to have there only stuff without that you would like to have there titanium only and calcium to it, or titanium and copper. So now you see this different here. Yep. Aluminum is also somewhere in the middle of it. Yep, so it's not very rich for aluminum. So you can do your element mapping really in a minute. It's not only about the mapping, but it's the biggest area, but you can use a line scan. So if you have different kind of sample that the elements of the composition varies in the line, so you can choose the areas, for example, through these boundaries, like that. Aluminum, copper, titanium, and calcium. Hopefully. So you see these grain boundaries are poor for titanium, for example. Yep. And you have bigger and bigger peak of copper here. So you can compare it also not by mapping or but also for line scanning. The same, it's a multi-point. So you compare different points. You will have a spectra for each of them. So you can compare quantification, the amount for different points, for different places. Or if you would like to have it, let's say, more like from a bigger place, so bigger with a better statistic, so you can put there different shapes and run it. Okay, this one I will delete. It's possible, not delete here. So if you put acquire, you will have these three spectra running in the same time, and you can compare the composition of each of it. Okay. So this is EDX. I will move it only to park position. Okay. So any questions for now for this chemical electron microscope? No? What about a small break now? Because later on I will change for focus ion beam and for gas injection system. So let's say about 15-minute break, and could it be? Yeah, okay, cool. Okay, so 15 minutes break. So let's say about half, or what is the time? I have different times here. I have 3:15 here, 3:10 here. I have to check This one, okay, 1515. So let's say 1530. See you here again. Yep. See you. Okay, sorry guys, I have very huge problem here with internet connection, so hopefully it will be now fine. So you can hear me, you can see me. It's okay?
Yes.
Yeah, okay. So I will show you the column is here, the electron column. So it's again the same cathode, the Schottky one, and it's going through the column down there to the sample. Here is really huge chamber to place their bigger samples. Moreover, we have lots of stuff here. So this one over there, it's a focus ion beam. So it's with a 55° to scanning to electron beam. Then these things down there, it's a gas injection system. So we have possibility of 5 gases to put into the chamber. The rest is the same. So here is a backscattered electron. Here is EDX, these broker ones. So you see it. So, and a secondary electron as well. So this is similar. Here is how the operations looks like. So we have, moreover, we have possibility to move with a tip. So how the chambers looks inside. So now it's better because it's much bigger. So the stage, oh, wait a minute, I need to close. I will be able to touch it. Yeah. So the stage looks similar, just the chamber, it's much bigger. Then here is again, it's electron beam column. From the side, it's backscattered electron. So you can check now in the reel that I'm moving, that is going in and back. So it's backscattered. These things over there, this is a secondary electron detector. And moreover, what we have here, it's EDX on that stuff right there. And we have, if I will go from the side like that. So here, do you see it? This is the electron column, and over there, the stuff on the 55°, yeah, that's one. So that's a focus ion beam. From the bottom one, there are nozzles of a gas injection system. And from a side, it's the tip. So it's manipulator. So I can move there back. You will see it then later on the camera. Okay, cool. So I will close the chamber. I put there several samples. One of them, it's a holder for transmission electron microscopes, lamellas. So I'm not sure you can see it, but yeah, I cannot. The resolution is really bad. So you will see it in a microscope. So I will pump the system. Okay, we are back. So I will pump the system and I will show you how the holder for these lamellas looks like. So here we have several of them. Okay, I will put the camera. A minute, I will take one of it. Tweezers. So here it is. I will probably like that. So it's this small stuff here. You see anything with this resolution, but you have to believe to me that there are 4 fingers where you can place your 8 lamellas. So very, very small stuff, but still possible to work with it. So I will pump the system and then you will see it in real stuff. Okay, I will check just internet connection if it's working. So here we are. Okay, and I will share the screen. Okay. So now I have 2 windows here. So you will see the both of them. So the right part is similar. Oh yeah, now it's somehow clicking because of sharing it. Okay, hope, never mind. It will not bother you a lot. So the right part is the same like for scanning electron microscope only. So here we have information about vacuum and about high voltage. So as I said before, there are possibilities to run from few of kilovolts to 30. Most of the time I'm using the most powerful one. Here again, information about pressures. Stuff for focusation, for alignment, the beam, the carousel, so the stage control, and your picture will appear here. Not yet, we don't have a good vacuum. So the left part is for focus ion beam. So we have similar focus ion beam panels, so we can choose energy as well. So up to 30 kilo electron volts. Then similar stuff for alignment. The left panel is something what we call drill beam. It's for milling and for creation the structure. And down there is the gas injection system. So as you can see, we have possibility, I said that we have possibility of 5 gases, but we removed fluorine from here. We are not using it for now a lot. It's most of the time, it's using for faster milling. So we are able to create structure from insulators, so it's silicon oxide. We use water, it's for faster etching of carbon materials. Then we have platinum and tungsten. It's bigger chamber, so we are waiting for vacuum a bit longer. Okay, probably I will try to do something with this effect. I will stop sharing and try to start it again. Share the screen. Okay, I can choose only one of it. Will it be better? Yeah, now it's better. Okay, so we will start even with scanning electron microscope. So I will share only right part, and then I will change it. Okay, I will move. Okay, here, if you will check a chamber view. So this is electron beam column. From the right is ion beam. These are nozzles from gas injection system. And here I will move with it up. Wait a minute. Okay. And here it's I put there just standard tungsten tip. So we will be able to move. And this part, it's moving now. It's backscattered electron again. So similar like the previous one. Okay. So I will go closer, just waiting for a vacuum. Okay, here we are. Okay, so for example, we will start with this one. It's a platinum doped cerium oxide deposited on a carbon material by magnetron sputtering. And from that reason, we have a porous structure because it's on a carbon material. So during deposition, we have deposition and etching in the same time. So again, in a few seconds, you have idea how your sample looks like. Okay, just simply to align the beam. So it will take a few minutes to align it. Okay. Just give me a minute to align it better. Okay, so here you can see your the sample surface. You see that it's porous, but to check the porosity even more, you can tilt the stage. So now you see it's moving. Okay, so we moved the sample, align it again. I'm moving it directly on 55 degree. It's perpendicular to the focus ion beam, which is here when you check the chamber view. So now it's perpendicular. And I will move closer. So, and as you can see here, now you have even more, you can see the effect of your porosity of your sample structure that is not flat. You can see it even more. What is here really see that, but you can really see here that here is not in focus, here as well. Here we it's in the focus because the sample is tilted now. But you can check the stuff like you have holes here. So you can go in and check the structure. Yep. Here, for example. So you see your morphology even more pronounced just by simple tilting. Okay. So as we are, the focus ion beam need a better vacuum. So now I will work with this gas injection system. I need to heat the nozzles, the full reservoirs, capillary as well, which are bringing gases into the chamber. So I will warm their up. And sometimes from time to time you will hear same noise because we need to do outgas for the gases. But for that, unfortunately, we need to turn the beam off. Okay, I'm still waiting for the second one. It will be warm up. I will stop sharing and I will start sharing again. Both of it. Oh no, it's not possible to share it. Come on. I can share only first one or second one, but not full windows. Okay, I will share the first one. So here you see these different gases. So I will put out gas for platinum as well. I put insulator and platinum on. These are the gases which we are using the most. Insulator is deposited, so the silicon oxide is deposited very fast. Platinum is somehow stronger. So this is what we are using mostly. Okay, we'll try it one more time. Share screen. Oh, okay. Okay. Even then it's same problem there, but it's blick. I don't know what's wrong, but after a while you will need to see both screens, so we need to do it like that. Okay, till we are waiting, do you have any of you scanning electron microscope in your lab? And are you interested more to life science or to material science? So I have just one example here for life science, unfortunately, if somebody is interested in. Oh, in life science, sorry. Okay, I have some neurons here. And tissue for medical application. So we will work with them. If a bit both actually and life science. So we will work with this life science more. Okay, so it's done. So we will turn on electron beam and ion beam as well. We are waiting for beam energy, the ion beam energy of 30 kilo electron volts. While the electron beam, the emission is still on, till it's mounted by a series. For focus ion beam, emission have to be turned on for each session because of gallium consumption, as it's this liquid metal ion source. So it's heated each time. So we need to turn emission on. It's taking a long time. I hope it will work. Okay. So here we are. So now we have possibility to see the same by the scanning by electron beam and by scanning by ion beam. So you can easily recognize those structures. So this hole up there on the left part is the hole here on the right part. One more thing which you can recognize is this rectangle done by scanning by ion beam. It's just, it's starting to remove the material, and you can see it just very brightly. It's here. Yeah, also this feature here on the right side, this feature here. So we have to align it that we will have in a boat, we will have the same. Yep. So if I'm moving here with electron beam, focus on beam, it's moving as well, but we have to align both pictures. So let's say this structure here, current, we have a problem with emission. Okay, so I'll turn it on one more time. We will see. Sometimes it happens when this small droplet of gallium, it's not formed well on a tungsten tip. So sometimes we need to do a procedure to put higher current there, or even to heat it for a while for a higher temperature, that the gallium drop will be formed really in a good shape. Okay. We will try it. Okay, we have different contrast. Okay, so here we are. So we have to align it more or less. Okay, so it's this one. Okay, feature. Okay, this was too huge. Cool. I will just measure current if everything's fine. Okay. So we can go closer. You see that resolution, it's here, it's much worse, like for electron beam, because ions are with a huge mass, and also the ion beam, it's not focused so well like electrons. So the resolution, it's much worse here. Even when we move, because I'm not choosing here only the ions energy, but also different aperture are responsible for different current. Here is what I have now. I have only 100 picoampere, but when I will move to the biggest aperture, which we are using here, You will see the picture will not be so nice. Up, not at all. I have to align it faster. Okay, moreover, it's somehow moving. Okay, we have huge astigmatism there. Let me check it. Yeah. Okay, really huge. Okay. Okay, it's a bit better, but still we have really huge energy here. If I will measure the current, it's about 17 nanoampere, so it's really, really huge one. But on the other hand, it's really great for creation the structure. You can see here, I was only focusing and I already removed material. If I compare it with SEM, so here you can see it, how I removed part of it. So for this thing, I have here this draw beam. You can draw whatever you want, like a line. You have different information here, like where to put the line, the size, it will be 0 and let's say 20. So like that. And here is the depth. So here we can choose a material which we are using. So we have carbon material, even that we have very thin layer of platinum cerium oxide. It's not so important for it, but the bottom part is from carbon. So, and when we will run it, you can see directly that we have a line here. We can create different structure. I put here field rectangle. Okay, it's too big. It will take 30 minutes, so I don't want it. So I will play with it. Okay, 2 minutes. I will let it run and I will stop it then. And it's scanning only in the area where you place it, there and back. So it's milling your material away. So it's creating structure which you need. At the same time, you can see that the secondary electrons, there is emitting so much particles that you cannot see the image. It's better for that. It's to turn the scanning off. And then to stop the process and to check it. Yes, so you already, we milled here. And we are going deeper to the structure. So I will stop the process. There is several possibilities. What you can do, there is a Polish rectangle. The scanning, it's different from the field rectangle because it's going in the direction of the arrows. So you are removing material by different scanning method, and you are removing material more gently. You can use stairs. So this is one what we are, I'm using mostly for a transmission electron microscope lamella. So you are removing materials mostly from this part, and the stairs remains here. So I will delete it. Also, you can draw whatever you want in painting and bring it here, or to write letters. Focus on beam, for example. Up. Move it somewhere. It's too big. I have to make it smaller. And I will move somewhere very smoother. Okay, it will done 3 hours, so really we don't want it. You see how fast it's degreasing. Okay. Something really, really small. I will just run it a few minutes, just that you will see that you have different possibilities what to do. Okay. Ah, yeah, it's already there. Yep. See it in here. Okay, it's nothing very scientific, but you can create whatever you want, just as an example. So what is the, okay. What is the typical why we are using it? It's this Lamellar Preparation. So you can save all your process about the lamella, how you create it. So for example, here you open it and, okay, I will go closer. And here it's protective layer. When you click on it, you have already 4 parameters like the size, the thickness. So now it's not a milling process, but it's deposition. You can choose it here if it's deposition or if it's etching. If you are creating several structures like these steps here, so you can choose if you would like to mill them one by one or at the same time. Here is the probe current, which characterize your beam, and then other parameters like dwell time. It's about how long the beam will stay in the same position, overlap, if the 2 places are overlapping, or if there is any bigger gap. It's different for deposition and it's different for etching and so on. So, and here it's your time and so on. So I will place there smaller aperture. Oh, it's running something. That we will have better resolution. Okay. And I will move from this material science. I will move to tissues. Here are some silicon tissues. This black part with the holes is carbon tape. So here we have same tissues for tissues engineering. I will just focus on it. So, and sometimes you would like to analyze them on TM, but you cannot analyze the whole bunch of it. So you would like to pick up only one of them. or you would like to study their conductivity, for example, or strength, or others things, other characterization. So how to do it? So we have possibility to pick up one of them by the tip. So first of all, I will move out and I will show you the tip. We have to find it if we have it. So here you can check it on this chamber view on the right side. You can check that I'm moving with nanomanipulator. Okay, something is coming. And here in this scanning electron microscope window, you can check that we have a tip. It's not in focus now. I will scan faster. Okay, so here we are. Here we have this tungsten tip. Yep. So if I would like to pick up something, I will just check it. It's here. Yep. Also in focus and beam window. So if I would like to pick up one of this cube, so I have to come with the stage closer. So first of all, I will go up with tip. I will bring back the sample. And now I control X and Y position by scanning electron microscope, and I will check the Z position by focus ion beam. Okay, you can see that we are coming with tip closer and closer by focusing it. So it's here. By FIB, it's not here yet. Maybe a bit because we have some movement. So we were probably touching. It's maybe moving under the beam. Okay, so we are going closer. Okay, we are touching already some of them. Yeah, and you see now in focus ion beam window, you can see that we have a tip here. Okay, we are moving. Unfortunately, we didn't touch only the one, but we touched some bunch, which was a bit upper in a Z position. Yeah, so we have something which is really up here. So now you can see it even in a scanning electron microscope window that we are moving with this bunch of it there and back. So if you will be lucky, you will touch only one of it and you can fix it by gas injection system. So you can fix it by SEM material. You can fix it there. Okay, I'm just playing there and back. I'm not very patient here. So sorry for that, that I'm not able to pick up only one, but okay, I'm only playing with it. And when I will go even closer, so it means downer in this position. So you can see that I am now closer to the carbon tape. So closer to the holder. So I can move more tissues up. One more time down. Yeah, so I have lots of them. I'm moving them. Okay. So I will show you now how it's able to deposit the material. So when you will come close enough to one of these tissue, so you can fix it. For example, now we have one of it somewhere here, so we can fix it by, now it was running out because of charging effect. But when we will be able to touch something, then we can fix it on a tip to pick it up or to cut it, whatever we want. Yeah. So for now, I will move the sample back down. I will place tip back home. And I will come back with a sample. Okay, so here we are. Okay, so this deposition process, I will show it to you on this Neurons sample. So here we are. We have a field of contacts. It's gold. They are gold contacts, and on them there are some cells. The main goal on this research was to see how these cells likes the contacts. So there were prepared several different sizes of those contacts and several different with different distances between them. So the one here, it's with distances which were too big. So if you check these cells, they are lying between the contacts and not on top of it. But for our purposes, never mind. I don't know which one. Okay, this one, for example. So we will focus it. Okay. Yeah. So again, we have to find the same position. Okay, something bigger here. It could be this one. This nice one, probably this one. So, okay, and we will move with this one. Okay, so now it's more or less in the same position. So a bit of focus, but not on the structure, which we would like to see, because it could destroy it a bit. Okay, so here we are. Okay, and now we can bring these nozzles. So let's say we will place their silicon oxide on top of it. So you can check it, this gas injection system here on the right in this chamber view. It's now moving. And it will appear here in scanning electron microscope window. So here it is. So here we have this 5 nozzle. I have to move it because silicon oxide is one on the very right. We will check position in focus ion beam. So we have to come a bit closer. So here we are. So this one on the right, in the right edge, it's the one which we would like to use. So we will go closer. And here we will put the protective layer on top of it. So we can create the structure like field rectangle through it, to choose deposition, to choose material. We are using silicon, okay. So we can do it by that way, or I'm using already one with already parameters which were done already. So, and here we click on insulator and we will open the valve. And now the gas is going to the fold chamber. The nozzles are close to the sample, but still it's in the fold chamber. But as soon as we are starting to scan on the top, the gas is decomposed only on the place where the beam is scanning. So it's decomposed and the organic part is pumping away by vacuum system, and this silicon it will remain there. Hope so. Hope we are close enough. Hope we have good current parameters. So I will stop it and I will check it by SEM. And yeah, you see it, right? It's this silicon oxide protective layer. So I will I will deposit it a bit thicker. Okay, let's check it. To study very surface of a samples, we are not using only this ion beam induced deposition, but also electron beam induced deposition. I will not show it to you today because it's time consuming. To create a protective layer by electron beam will take about 10 minutes to wait. Sometimes even this 10 minutes, it's not sufficient and we have to run it twice. But this procedure, it's less invasive, so it's more gentle because even so that we are calling it protective layer, first it's going to a very few layers of your samples. So if you have a surface structure like few nanometers, you have to protect it by electron beam induced deposition. So for whole lamellas, which we are preparing for transmission electron microscopy, we are using this electron beam deposition first. And by this process, we can study even layers which are 1 nanometer thin. Okay, let's stop it. Okay, it's thick enough. So we will close the valve and we will park the nozzles back. We'll check it in FIB as well. So you really see it, that your protective layer is here. I will move now to bigger aperture. I just have to focus it again. Okay, it's moving there and back. So I have to align it. Okay, better. Maybe one more. Okay. Okay, so now we have more current, so about 1 picoampere. Usually for creating these steps, I'm using even bigger aperture with about 10 nanoampere. But here, as it's it is okay, I will just turn the process on. It's a life science, it's carbon, so I'm afraid to destroy it if it's not too delicious. So I use rather smaller current, and I will run it several times if possible. If not, if it will not be sufficient to mill it, these materials out of it, so then I will use bigger aperture with more current. Okay, let's check it. Okay, so you see it's starting to disappear, or it's a bit slower. So let's move to bigger one. Hopefully we will not destroy it. Because it's really too much. I'm not sure. I will try to put less here. Okay, even be fine. Okay. Okay. So here we are. I will try it. Hopefully we will not destroy it. Okay, it's running fine. Okay. Maybe one more. Okay. So here we lost material contrast because we have now this protective layer here. You can see slightly the difference somewhere here. But we lost that material contrast because of redeposition. For sure, we have milling effect. We mill material away, but this material, it's not running totally out of it. Same of it, it's redeposed back. So we lost material contrast here. So we will polish it. I will put now the one which is not so huge. It's worse. Okay. And I will polish it. And hopefully we will have material contrast there again. Okay, I'll check it. Okay, you can see here it's much better now. We have this material contrast again, so we are putting out this redeposition layer. If we are using smaller aperture, we can even see the process directly. Sometimes it's possible when you use smaller current. Okay, it's done. So now we will go closer. You can really see, okay, with secondary electrons, it's hard to see material contrast, but still here it's partially able. So this is your protective layer. Here it's this neuron cell, and then it's a substrate. So it's an oxide on top of it, and then there is a rest of substrate here. If you would like to prepare a sample like this one for transmission electron microscope, you have to continue and you have to cut it from the side and undercut. So I don't know how we are with the time. I think fine. So we can continue in this process. Just for this one, I need bigger holes around. So I will move back to this bigger aperture. It's somehow wrong. Okay, now it's better. So I will run these stairs one more time. That we will go deeper, that we will be able to undercut it and to pick up the lamella. Okay, I'll check it. Okay, it's enough. So we will move back to this more gentle one. So we already polish it. So now we use a simple trick that we will turn it to 0. So here it is. So here is our top view now. You can see only protective layer. Now it's about a bit difficult how to compare this picture with the previous one or with the secondary electron image, because we are with the sample holder, we are on a 0 now. So scanning electron, the electron beam, it's perpendicular to it. So we are seeing it from the top of it. But focus end beam, it's now 55 degrees to the sample holder, but it's not 55, it's from the back. So you can see a back part of your sample here. So now we will cut it from the side and undercut it from the bottom. So now it's the analogy with this cake. You need to undercut it to see it. What do you have from the bottom part? So I will let it run. Okay, we are probably, I put it probably too far because we can see the line here. I'm not cutting the lamella, but I cut, okay, so I will go, I cut the substrate, so I will put it here. So one more time. Okay, it's taking more time than I thought. let's say 5 more seconds, and I will check it if it's cut or not. Doesn't seem so. Seems that it's too thick. So we will check. If not, I will let it be and I will show you something more interesting because it should be boring for you, isn't it? Okay, is there? Okay, it was almost done. You see the line on the bottom? So it was almost cut there. So the next step would be to come with a tip, to fix it on a tip, to cut it from the side, and then you will pick up the lamella and you will fix it. I don't know which one I have it. Is that one? Yep. You will fix it on your sample holder. So here is the sample holder for transmission electron microscope. So for each of this finger, you can place one lamella from the side, and then you turn it off and you can put another one from another side. So you can place 8 samples in a row to the TM. So when you have, for example, session for a longer time for TM, you don't need to put it in, put it out. So it's better for a vacuum, better for so you will have less contamination, etc., etc. You are not manipulating with a sample there and back, so there is less change than you will destroy any of them. Yep. So what next? Maybe the tomography could be. So if you don't want to make a whole lamella, if you don't have possibility for a TM session, and still you would like to see how your sample looks like, you can do tomography. So you can run, I don't know, I have to find a nice one. Oh, there is a big one, not that one. So for example, this one. Yep, nice one. Okay. So you can run, where we are. Okay, this one is it. So you can do tomography. So sorry, I forget to save it. So now I have to focus it one more time. Okay. So if you are not interested, you're putting only on one part of it, for example, like here. With or without protective layer, it's measured on your sample. Okay, let's check it. Okay. Have a hole now. We cut part of these neurons, and now we can put we will put this polishing rectangle, maybe 6-1. I will check it. And you are moving step by step. You are removing material. You are acquiring pictures, and you will have full information about these neurons. How does it look like? I will just check if it's enough, this current. So now we removed part of it. You can acquire the picture, and then in some tomographical software, topographical software, you can place everything together, and you will have information how your neurons looks like. So now, even without any huge material contrast, we can see same pores here. So if I will acquire it, and I will compare it with the next one, you can check it, and amount of images and how big steps for this polishing you are doing, it depends on your own preferences. Okay, so let's save it somewhere. Okay, now we can continue. Let's check it. Any difference or not yet? Maybe I will run it a bit longer. Okay, now we really see the difference. So it was the first one. And here is the second one. So we can see more pores. So if you are interested, for example, only on a small part of it, how does it looks like? You can focus, go even closer with bigger magnification. Even now we can go closer to focus on those structures of the cells, and then later on to polish it more and to acquire next picture and to place everything together to make a huge stack. So for example, here you see that adhesion with surface, it's not very well in these places. Here it's better. Yep. So that was this tomography. Do I have any other samples there? I have tissues. Not this one. Oh yeah, it was a chip. Just an example that you can study also. Same chip failure and so on. So you have contacts here and you can check them, and also to make a cut to see if it's if there is any break or not. Okay, I have no more ideas what to show you. Do you have any questions? Is there somebody, or are you sleeping? Okay, go back here. Okay, so it's really fast and way how to obtain the sample, how you can create lamellas for transmission electron microscope. It's really invasive and it's really fast. And you have several possibilities. And we offer access through this CERIC consortium. So do not hesitate to write a proposal. So if not the case, I will turn the microscope off. So it's also done in a minute. So it's also fast to remove the samples to put another one. So in a short time, you can check lots of samples with different properties. Okay. So if not the case, that there are any questions, so I will stop sharing the screen. So thank you for your attention.